Welcome one and all to another exciting day of AP Statistics. Today we're going to finish chapter 12. So what we're going to be doing today, what if I have two proportions, right? So similar to what we did back in chapter 11 when we did the two sample T. Now we're going to look at, well, what if I want to compare two different proportions? Okay, now cut that out. All right. So to get our confidence interval, as always, it's our statistic. So in this case, it's the difference in our two proportions, plus or minus our margin of error. Now to get our margin of error, we're using a Z. Okay, so we're going back to Z. And then that critical value gets multiplied by, of course, our standard error. Here's our standard error formula. Okay. And this, again, should make sense because that is the variance of one plus the variance of the other, right? We can add variances and then we square root. You don't have to memorize it. Okay, there it is on our formula sheet. Again, clearly labeled for two populations. And there we are, the difference in the two proportions. Okay, and notice here we're using a sigma, whereas over here we're using an S, right? Standard error S. Sigma is if you have the parameter, right? It's why there are hats over here, there's no hats over here. So anyway, there we go. Okay, in order to validate our test, our calculation, it's basically the same checks as always. We need good unbiased data, so if we have an SRS, we're there. Our population has to be at least 10 times the size of the sample. In this case, we have two different populations, right? So each one has to be at least 10 times their respective sample size. And then normality, okay? You will recall the n times p at least 10. Well, now that I have two different p's and two different n's, that means there's four different combinations. So instead of making them all at least 10, we're saying each one has to be at least 5, okay? And that can differ from one textbook to another. So for our book, they're saying each of those are at least 5. Okay, as those numbers get larger, right, we get more and more normal. So it doesn't hurt if they're at least 10. That's good. That's a better thing. And on the AP exam, again, since different books have different criteria, just write what it is you're checking, and they'll say, okay, that it passed their checks. Now, of course, you can't make up your own, right? Don't say, oh, each one is at least 1. That's not okay. But our book says each one at least 5, so that's fine. All right, if we're doing a significance test, null hypothesis, two proportions are the same, or they have a difference of 0, right? You could say it either way. Alternative, again, could be one or two-sided, depending on the question. Now, last chapter I said, just say no to the pool, right? Just stay out of the pool. Now is the time we get to go for a swim in the pool. So here's where we pool, okay? When I have a significance test and I've said the two proportions are equal, and our whole calculation is based on the assumption that the two proportions are equal, then it doesn't make any sense to keep them separate. We may as well pool them together. So to get our pooled sample proportion, we simply look at the total number of successes through the two samples, and we divide by the total number of observations in the two samples, and that's our pooled proportion. Okay. Our samples will have subscripts 1 and 2, so we know which population they came from, and that's what we're comparing. Okay. When you remove the subscript, that means we're talking about the pooled, okay, when we have two samples. Okay. So that's how we can tell them apart. Okay, significance tests also need to be validated. Our conditions, again, good unbiased data, so some type of random sampling. And again, each population needs to be at least 10 times the size of the sample. And for normality, our book goes with all of the following expected counts, at least 5. Notice for the confidence interval, it's observed counts, right? For the significance test, it's going to be expected counts, okay? And notice the expected counts here are based on the pooled proportion, okay? Not the samples, because these are expected counts. Okay, so that's different. So here we have a difference in our normality check between significance tests and confidence intervals. Common place to make mistakes on the test. And lastly, here is our formula for our significance test. Again, note it's a Z. Okay. And as always, it's our statistic minus the parameter, which would be, well, it's not on this page, but minus the parameter, which would be a difference of 0. So you don't write the minus 0 unless you really want to. And there is the standard error, and there it is on the formula sheet. And it even says, when P sub 1 is equal to P sub 2 is assumed, right? So when that's your null hypothesis, that's what you're going to use. Okay? And there's the pooled. Tells you how to find the pooled. So they labeled the pooled with a subscript of C, so they're reminding you, hey, here's how you get this proportion to use in this formula. So it's right here. It's all very clearly labeled for you. Okay. Our book doesn't use a subscript. We just say if there's no subscript, that means it's the pooled. All right. Let's try a problem. Okay, so in a nursing home study, researchers found 12 out of 34 small nursing homes had a vaccination rate of less than 80%, while 17 out of 24 large nursing homes had a vaccination rate of less than 80%. At a 5% significance level, test the claim that there is no difference in these proportions. Then find a 95% confidence interval of the true difference in the proportions. Okay, so our checks. Doesn't say how the data was gathered, right? So we should mention we assume an SRS was used to collect the data. If a different method was used, it could invalidate our results. All right, so again, we need unbiased data. Okay. As far as population size, we have a ton of nursing homes out there, so that's fine. We have 340. Okay, so it is safe to use the standard error formula. Okay, so same checks we've been doing for a long time now. Okay, lastly, the normality checks. It depends which calculation we're doing, right? So we're going to do a significance test. So we'll do maybe for this test, probability or proportion of small is equal to proportion of large. No difference, so right. So for that one, we got to get our pooled, and then we can use that for the normality checks. So let's see, 12 and 17 29, sorry, out of 58. So, oh, 50%, that's easy. Okay. So our checks here. What was our first sample size? 34. And our second sample size, oops, P hat, was 24. Okay, so from our book, we'd say all of these are at least 5, and it turns out they're all at least 10. So if you were using a different book, you'd be fine with that. So all expected counts are at least 5, so we may assume approximate normality. Right? That's what's allowing us to use the Z. Sometimes people forget why we're doing these checks. This is so I can use my Z, right? This whole calculation is based on being normal. So that's why it's important. Okay, let's have a little space here. Let's do the check for, or the checks for normality on the confidence interval. So for the confidence interval, it would be what was that, 34? And second proportion, okay, notice these counts are different. That's why we have to do the check. Sometimes you might pass these and fail these, or vice versa. So you got to do them. You can't just say, see the checks from above, right? They are different on the normality, so make sure you do them. If you just write see the checks from above, you're going to lose some points. Okay. Now, these would be all observed counts. Or at least 5. So we may assume approximate normality. Right, of the sampling distribution, right, of the proportion of, right, blah, blah, blah. Okay, so hopefully that's clear. Let's do our calculation now. So first we were doing the significance test. Okay, and a little short on room. You know what, I'll just unveil it. There we go. So this is, well, I like writing the proportions in there, so I guess I'll rewrite it over here. So our Z would be 12 out of 34 minus 17 out of 24 divided by, here's our pooled, right? And our pooled was 29 out of 58, 1 minus 29 out of 58, 1 over 34, 1 over 24, right? So, right, there it is with the fractions. And I like writing it with the fractions. That way you see where the numbers came from, right? So here it is with some decimals, but it's the same thing. So we get a Z of negative 2.67. What's the degree of freedom there? Aha, trick question, right? We're doing a Z, so it's the infinity row. If you were using table C. But of course we would be using table A because it has more accuracy than table C if I'm working with a Z-score. So working that out, we should get this for our p-value. Now let's do it on the calculator real quick. This is a 2 proportion Z test. There it is, clearly labeled. And let's see, our first X was 12, 34, 17, 24, and two-sided. There you go, there's your Z, there's your p-value, and the two p-hats, sample sizes, all that, pooled proportion, it's all good. And there you go. That's how you do a two-proportion Z-test. Hopefully easy. Now, let's do our confidence interval. Oh, sorry, forgot the conclusion. Here's our conclusion. That's a really small p-value, less than 1%. So we're going to reject the null hypothesis and say we have strong evidence, or even very strong evidence, that there's a difference in the vaccination rates between small and large nursing homes. Okay? All right. And our confidence interval. Okay. So we're doing a 95% confidence interval. We get to use Z. So we get to go back to our favorite table and use our favorite row, the infinity row, right? So you may remember that number, 1.96, as our critical value for a 95% confidence interval using Z. Okay. So there's the 1.96. To get this is of course the difference in the two proportions. So that's 12 out of 34 minus 17 out of 24, right? That's how we got that. And here we have all the fractions there. There's our interval. Are you surprised that both these numbers are negative? You shouldn't be, right? Because we got a very small p-value telling us that there very likely is a difference. And that's why both of these values are negative, because there's very likely a difference. Okay, it's very likely that the large nursing homes have a higher vaccination rate. Okay. All right, don't forget to write your conclusion. Hopefully I have that on the next slide. I don't. Okay, so our conclusion. We are 95% confident that the true difference and proportions between small and large nursing homes is between side note, if I try to use this confidence interval to do a significance test, remember, we do have a slightly different standard error, right? So if 0 is just inside or just outside of this interval, we really can't conclusively use the interval, right? Because, again, the difference in standard error. If 0 is a long way outside or a long way inside, then, yeah, it's pretty safe to just say, yeah. Use the confidence interval to do your significance test. Okay? All right, let's try another one. Okay, this time we have a simple random sample of 50 men with high triglycerides. They consumed 2 tablespoons of oat bran daily for 6 weeks. After 6 weeks, 60% of the men had lowered their triglyceride level. Okay, now we have a separate simple random sample of 80 men. Right, this is why it's a 2 proportion. We're not going to be matching these subjects up in any way. They're 2 separate populations. Okay, this population consumed 2 tablespoons of wheat bran for 6 weeks. Okay, and the wheat bran group, only 25% lowered their triglyceride levels. Okay, so is there a significant difference here? So in other words, is oat bran or wheat bran, right, different in lowering triglyceride levels? Okay, this is important research. You would, as a doctor, want to know the answer to this. So when you have a patient with high triglycerides, you would tell them, hey, you need to eat this. It's a better choice to lower your triglycerides. Okay. All right. So conditions. It's given that we have an SRS. Our sample sizes are both large. There are easily 500 men with high triglycerides that consume oat bran, and easily 800 men with high triglycerides that consume wheat bran. So safe to use a standard error formula. And our counts, I'll do those because that's kind of new. Let's do our counts real quick. Got to get our pooled proportion. So, actually, notice they gave me percentages. They didn't give me the proportions. Let's find our proportions real quick. We have 60% of 50 men, so that means 30 out of 50, right? Here we have 25% of 80 men. Okay, so that means 20 out of 80. So there's our proportions. Now we can do our pooled. So 30 plus 20, 50 plus 80. So there's my pooled proportion. Okay, now for my normality. Okay. So we have 50. And the second sample size was 80. Did I work those out yet? No, they don't work them out. Okay. And notice, you can have expected counts that are fractional. That's fine. You can't have observed counts that are fractional, but expected counts can be fractional. So. Okay, so there's my expected counts. They're all at least 5. They're all at least 10 as well. So. Okay. All right, so now let's do our actual significance test. So our null hypothesis, the two groups have the same proportion, right? Alternative, I don't think it's specified a direction, so alternative two-tailed. Yep. And I don't see the work on the Z, so let's show the work on the Z. Okay, so the difference in our proportions. Okay, and your formula. Okay, we've got a pooled problem, right? Because we assumed they're equal. So here's where we use our pooled P, which was 50 out of 130. And there we go. So that's how we get the Z, and apparently it is 3.99, and our p-value is very small. Okay, and doing it on our calculator. Two proportion Z test. We have 30 out of 50, and we have 20 out of 80. And by the way, a lot of students, since this problem gave you the actual percentage or not the raw count, a lot of students try to enter, 0.6 and 0.25, and the calculator will tell you error because the calculator requires that these are whole numbers because that's how many. These are counts and sample sizes. You can't put in decimals. So there we go. There's the same z we got by hand, same p-value. All right, so conclusion. Really small p-value, so really strong evidence that there's a difference between oat and wheat bran at lowering triglyceride levels in men with elevated triglyceride levels. Okay. Yes, I wrote it out. Haha. I don't have to write it now. Okay. And moving on to our last problem. Okay, let's do a 95% confidence interval for the two difference in proportions for the data of a study in which 40% of 200 males surveyed opposed the death penalty and 56% of the 100 females surveyed opposed the death penalty. Okay, so checks. Doesn't really say how the survey was conducted, so assume the survey used random sampling methods. Or else our results could be invalid. Again, good unbiased data. All right, there's plenty of population size for this, right? There's at least 2,000 males and 1,000 females, so safe to use our standard error formula. I'm not going to write that. We've done it a million times. Okay, and lastly, let's do the normality checks, because again, that's kind of the common mistake on this particular problem type, okay? Because we're doing a confidence interval, our normality check will be the observed counts. Okay, so here we are. Again, they gave me percentages, so 40 out of 200, that's 40% of 200 is 80. And 56% of 100, well, that's 56 out of 100. Okay, so 200. Okay, so again, these are the observed counts, right? 80 of the men said they opposed the death penalty. That means 120 didn't, right? That doesn't mean they support it, by the way. It just means they don't oppose it. And then 56 of the females said they opposed it. 44 did not say that. And again, these observed counts are all at least 5, so we may assume normality. Okay. And again, that's the check that for some reason gets messed up because it's a little bit new and different, right? The other two checks everybody, hopefully at this point in time, has down without issue. Okay, let's do our 95% confidence interval for the true difference. So our first group was 80 out of 200. Our second group was 56 out of 100. Plus or minus 95% confidence. Again, we get to use Z, so 1.96. And our, where were we? 80 out of 200. 56 out of 100. There we go. So there's the work. Now I'll use the calculator. There we are, 2 proportions, Z interval. 80 out of 200, 56 out of 100. Confidence was 95%. So there's our interval. Notice they're both negative, so probably a significant difference between the 2 genders here. But that one is starting to get a little close to 0. So if you were doing a significance test, you'd probably want to actually run that significance test. And even if 0 were well outside the interval, not a bad idea to find that p-value so you know the strength of the evidence, right? Okay, so lastly, conclusion. Conclusion isn't written. Okay, let's write our conclusion. We are 95% confident the true difference in proportions between men and women that oppose the death penalty is between Oh, and again, some people still are kind of misinterpreting this, right? The interpretation is if I went out and I repeatedly sampled the same sample sizes of males and females, and I then did all these calculations over and over and over again, excuse me, 95% of the intervals that I find would capture the true difference, okay? It's not this one interval, right? This is one of many, many intervals, and 95% of those intervals out there calculated using this method, this 1.96 standard deviations, will capture the true difference. Okay? All right, that's it for the chapter. Study up, and good luck.